My name is Jakub Gałecki. I think my presenter name in the get response webinar system is different, but that's just that's unfortunate. But my name is on the screen in the presentation. Can you guys see the presentation, by the way? All right, I think perfect, wonderful. Great, thanks. All right, so I wanna give everyone just like another minute to join up if they're coming late. So just some general points about today's webinar. I'm going to be talking about radiative heat transfer in our toolbox, in our toolbox. So first, I'm just going to talk a little bit about the underlying equations and the model that we're using for simulating radiative heat exchange. Then I'm going to present two cases. So one is going to be well, real life, maybe putting it a little bit too strongly, but I feel a fairly complex example which should illustrate a lot of the features of the toolbox and of radiative heat exchange in particular. And then I'll illustrate a sort of more hypothetical example just to show you guys some of the issues that may occur and how to stabilize your solutions, how to reach convergence, etc. Just some tips and tricks, just sort of so you have an idea maybe why your simulation isn't converging. So right now I can see the chat, but just as a heads up, when I'm in MATLAB later, I think my chat is going to be hidden. So please save your questions until the end. There's going to be a Q&A at the end, so I'll answer all of your questions then, hopefully. Okay, so it's 3 past the starting time, so I think we're going to get started. All right, so once again, welcome. My name is Jakub Gałecki, or you can call me Jacob. So in today's webinar, I'm going to be talking about radiative heat exchange in our toolbox. So as I said a second ago, first I'll just talk a little bit about the underlying physics of radiation. Then I'll talk about the configuration factors, what they are, and how they relate to our model. Then I'll talk a little bit about the heat transfer equation itself, so sort of the grander physics underpinning our solver. And then just a really quick recap of the Navier-Stokes equation, since we're going to be solving a case that involves both fluid flow and heat transfer. So just sort of, so everyone has an idea of what's happening with the fluid flow. All right, perfect. So basically, radiation is a way that objects exchange energy in the physical world. Unlike other forms such as convection or diffusion, radiation does not require any sort of medium between the two bodies. So the most obvious example, there's vacuum between the sun and the earth, and yet we still feel the sun. So the equation you can see here, this is the radiative power, so to speak, of a body, of a black body, defined by the or with regards to the temperature of the body and the wavelength that we are considering. So radiation is sort of a multifaceted phenomenon. So obviously it occurs in the space-time continuum, but also often different materials have different properties for different wavelengths that they emit or absorb. So this is also sort of something you have to take into consideration usually. We have a somewhat simplified model. We just consider the radiation globally. We neglect any spectral phenomena or spectral properties that our materials may have. So once again, this is the power per wavelength, sort of. So if we integrate this over the wavelength, so from obviously from 0 to infinity. Well, the calculations are fairly complex, and it's not really the point of this webinar to get. But suffice to say, we get this this formula for the total black body radiation. I'm sure we've all seen this before, probably in like high school. Some very basic stuff. So the radiative power emitted by a black body is proportional to the fourth power of its temperature. And here you have the sigma, or the Stefan-Boltzmann constant, and here it is on the screen right here. Once again, basic stuff. All right, so this is basically the physics underpinning our radiative model. This is sort of these are all the radiative equations that we really need. The more complex bit of the solver is the sort of geometrical part. Since a flat surface does not emit radiation isotropically or the same in all directions, or the radiative power isn't the same in all directions, the radiative intensity is. If you, well, one job here is not to explain all the details of the physics. It's more to give you just a quick overview. If you guys can certainly look up the difference between intensity and power online. It's very it's basically radiation 101. I'm sure most of you know what I'm talking about anyway. So in any case, to determine how much radiation that is emitted from one surface reaches another surface, we need to calculate something called a configuration factor. The definition of it is just like I said a second ago. You have it on your screen, and it is this this very nasty integral that you have on your screen here. It is a sort of double integral, so to speak. So it's a double integral over two areas of one face, or yeah, one surface and the other surface. This is the general formula. In our solver, what we do is we calculate this view factor between every face mesh that we consider to be radiating. So later, based on the Stefan-Boltzmann law, we can calculate how much energy leaves each face and how much energy reaches every other face. And then we can basically impose a Neumann boundary condition. What we're essentially doing is imposing a flux through those faces. So actually, the way this integral is computed is fairly complicated. This is all under one function in our toolbox, which I'll talk about in a little bit. So you don't have to worry about any integrals. Obviously, we do this for you. Life is fairly simple and easy for the users. Well, calculating this is actually tricky because the best way to do it is to convert it to a actually not a surface integral but a boundary integral. But that has some issues too. So there are several cases considered in our function that calculates these view factors. Also, I should say this is a little bit different for 2D. This integral looks well, the distance isn't squared. Oh, I should probably mention what these what these values represent. I'm sorry. So theta 1 and theta 2 are the angles between the normal of one surface, or so the theta 1 is the angle between the normal of surface 1 and the point, the connection, the sort of the line connecting the 2 points that we are considering for the integral. I think maybe draw this so it makes a little bit more sense, because I think it's fairly, maybe it's a little too abstract to talk like this. One second. So, erase draw. All right, perfect. So let's say we have one surface and another surface. Sorry for the crude drawing. All right. So what we're integrating is something like this. So let's say this is the normal to the boundary, to the surface, excuse me. This is N1, and this is N2. So the length of this segment is s, so s squared is the squared length of the segment, and theta is this angle, so it's the angle between this line that connects these 2 points and the normal. So this is theta 1. All right, I hope this makes sense. So once again, as you can see, we have to integrate over both of these surfaces, and well, this sort of the cosines compound in a strange way, and it's very very nonlinear, and it's I don't believe, well, it definitely does not have a analytical solution for the general case, which is why we do it numerically for the faces of our mesh. So I mean, it has some analytical solution for some special particular cases, such as, for example, like a circle within a circle, or a sphere within a sphere, or some uh, like some I believe like cylinders between each other. There you can find these online. These are called, as I said, configuration factors, also view factors. Um, you can find some specific cases in books, but unfortunately, obviously, the geometry that you use for your CFD simulation is very far from anything that you can find in books. It's a triangular mesh or a tetrahedral mesh. All right, so I think enough about configuration factors. Let's move on. So as I said, the radiative fluxes are imposed as Neumann boundary conditions for the heat transfer equations. So just to kind of get through this quickly, what we're solving is we have the time derivative of the temperature. We have the uh, here the convective derivative. So this altogether is obviously the material derivative, basically, of T. The temperature. U here is the velocity of the medium that is convecting, the convecting heat. So like if a fluid is flowing, then obviously you're going to have convection. I mean, I'm sure you guys know all about that. And here we have the diffusion. This is actually, maybe I should highlight, because we're going to use we use the constant um, thermal conductivity, but this is actually like in real life, this is more like this. So here, if lambda, or the thermal conductivity, is not constant, then you have to also differentiate it. So I mean, this once again, I'm sure everyone knows what I'm talking about. Just to kind of quickly remind everyone what's happening. This case will not be considered in our cases today, simply because it's simpler that way. But in general, a toolbox obviously can handle if the conductivity is not constant. This is not any issue. And also we have the source terms. So what's really interesting for us right now are the boundary conditions. So first, the Dirichlet boundary condition. We just prescribe the temperature. Very very simple. Then you have the Neumann boundary condition. So you prescribe the flux at the boundary. This is of interest to us, particularly because what we're doing in our solver is effectively prescribing the radiative flux. And we have the Robin boundary conditions, or the convective boundary conditions. So this basically states that the flux through a surface is proportional to the difference between the temperature at the surface and a reference temperature of a medium that is possibly flowing past it. This is I mean, this is also, I'm sure everyone who had anything to do with heat transfer in school and at university knows what this represents. Okay, so I think we're ready to move to MATLAB. Are there actually, no, sorry, we still have the Navier-Stokes equations, but once again, just to get through this quickly, we have once again the material derivative of velocity, and here the convective part is nonlinear, which obviously is the biggest complication of the Navier-Stokes equations, at least when we're talking about laminar flow. The gradient of the pressure divided by the density, and then here we have the diffusive part. So here actually, what I wrote on the previous slide about also having to differentiate the viscosity, or in the previous case, about having to differentiate the thermal conductivity. Here it's written explicitly. Yeah, so I think everything is clear. So let me just try to start sharing my screen. So any questions regarding the equations or the model? Maybe I can explain the surface to surface model a little bit better. Do you guys have any questions at this point? Let me know. All right, no one's typing, so I'm gonna assume that we're gonna have some more questions at the end. So I think starting now, I'm not gonna have access to the chat. So please now save your questions until the end. All right, great. So can you guys see my screen? I think you can. Yeah, perfect. All right, so let me just put this away. And let's move to MATLAB. So the first case that we're going to consider is a radiatively heated channel. So let's just read and give it a look. Any second now. All right, sorry. This is a small geometry, so MATLAB is having some issues zooming in. We'll fix that right away. All right, great. So basically, what's happening here? Actually, 1 second. Let me run this script one segment further. I'll talk about the code in a minute. All right, great. So now we have the great. So this case is fairly simple. We have a pipe over here. This pipe is going to have a high temperature, I think like 1200 Kelvin or something like that. This is the point here is the channel, so the middle between these two boundaries is where the fluid is going to be flowing, and here on either side we have the actual solid channel geometry. The properties taken for these are, I think the pipe is the properties are those of copper. The channel is steel. I don't remember which steel. It's not particularly important. And the fluid that's going to be flowing is water. So what we're going to model is the pipe is going to be radiating because it's very hot, and it's going to be heating this top wall of the channel. And then the fluid inside, the water, is going to be in turn heated by this part of the channel. So we're going to do a full simulation of heat transfer combined with fluid flow. And also because the way I define the viscosity is that it is dependent on temperature. The viscosity of water actually between the range of like 0 Celsius and 100 Celsius, so between freezing point and the boiling point, changes significantly. I think it's like threefold basically. So it is a non-negligible effect in real life. So because the viscosity is not constant, it is defined by the temperature. We're going to need to iterate a few times between the heat transfer and the fluid flow. So to develop a full solution problem with inhomogeneous viscosity. All right, and maybe it'll be a little bit more clear if I display the mesh. All right, wonderful. So as you can see, maybe not this much. All right, anyway, so you can see the channel is the sort of greenish, I guess, the greenish domain. The yellow domain is the water, the fluid, and the pipe here is, I mean, it's supposed to be blue, but the mesh is so fine that it's actually black. But anyway, the circular part up here uh, is the is the pipe that's going to be heating the system. All right, wonderful. Uh, so maybe actually let's take some questions at this time, just to get back here. Do you guys have any questions? Is anything unclear? Um, so what code? The code is the QuickerSim CFD toolbox. This is the product that our company develops and publishes. So I'm going to talk about meshing later because that's for the Q&A. But we make our meshes outside of MATLAB. But once again, I'll talk about that later. Is there anything unclear about particular case? Maybe should I explain something a little bit better? All right, someone is typing, and okay, so no one is typing anything right now. So I'm gonna. The mesh for the pipe is only for the outer surface, I believe. No, it's just fairly fine. If you zoom in, you can see it's for the actual geometry. Yep. It's just the way it's like a very elongated geometry, so you can't really, I mean, you can't really see the mesh from out here because it's very fine, so it's just black lines that blend together. But it's an actual mesh, I assure you. All right, so let's move on. Um, okay. So what we did in our code so far, as we read the mesh here from this is the mesh file that I saved earlier. We scaled it just because I created the mesh in units that were sort of more convenient for the mesh generator, and then we assigned the boundaries and the physical IDs of the domains. So you can see here. Uh, this is just sort of so I'm not using numbers, so I can use the sort of the names to define my boundary conditions later on. Once again, the physical ID of the pipe is 1, of the channel, so if the solid, the metal, the steel part is 2, and the water, the fluid is 3. All right, so what we did next is we generated an interface between the fluid and the solid parts of the mesh. In our software, basically, you can't create interface in the mesh generator. You do it in the actual solver. This is because I mean the solver needs a little bit more information than what the mesh generator provides. However, as you can see here, this is a very simple function. So PET are the arrays containing the mesh. If you've worked with our software before, I'm sure you're familiar with these arrays. They just define the mesh. P is the coordinates of the nodes. E defines the edges or the boundaries of the domain, and T is the connectivity list between the elements, or the topology of the mesh, essentially. So yeah, just what we did here is we defined the interface between the fluid and the solid part. The ID of the walls that we created is 23. And once again, if we call our display function here, as you can see on the side, you can see the IDs of the boundaries here. So the inner pipe is 4, outer pipe is 5, etc. This is important. I figured this out in the code myself. You guys don't have to really follow which is which. I'm sure you'll be able to tell what we do at each boundary later on from the sort of physics of the problem. All right, then we convert our mesh to the second order. Because our software is based on the finite element method, we have to we solve our velocity problem on the second order mesh and our pressure problem on the first order mesh, essentially. This is due to something called the LBB condition, or the inf sub condition. It's basically it's a mathematical theorem which specifies function spaces that you need to define, you need to choose for your approximations so that your pressure solution is unique. You don't really have to worry about that. Suffice to say that we use the second order approximation for our velocity and a first order approximation for pressure. Okay, so yeah, and the n fluid nodes is just a number of fluid nodes. It's very simple. All right, so what we do next, yeah, let's run this part. Actually, let's run this from the beginning. Sorry, just to be sure. And convert mesh to second order. Okay, so here we define our material properties. So as I said before, this is the K is the thermal conductivity, and rho H2O and Cp H2O is the density and specific heat of water, respectively. This is, by the way, this is all in SI units. This is all in metric. There's well, I don't think anyone who doesn't need to like to use the imperial system. So let's just stick to metric. What's important is actually you need to use metric because the radiative solver later on, the Stefan-Boltzmann constant from earlier, is defined in it's in watts per meter squares per meter squared per Kelvin to the power of 4, I believe. So you need to use metric in any case for radiative. I mean, you can conceivably scale your solution accordingly, but it's just use metric, please. The world will be a better place. Sorry. Anyway, so here we just define the material properties. As I mentioned before, load the properties for water. So here you see load H2O viscosity. New. So here, I hope you can see that this is actually a function handle. So this is not a constant value, as I mentioned before. This is a function handle to a function which takes the temperature of fluid or water and returns the viscosity. So we can just really quick draw this. So let's say T equals 280 to, let's say, 370. And let's just plot this real quick. So this is basically the viscosity. As I said, it is quite substantially over the range of. I mean, this isn't even 0 degrees Celsius. These are in Kelvin, by the way. Just I hope this is obvious. All the temperatures I'm going to be using today are in Kelvin, because the radiative fluxes are computed based on the apps temperature of a body or a surface. So as you can see, over the span of like 90 degrees, the viscosity of water changes more than threefold. So this is a very important effect. We're going to neglect any compressibility of water. It's very small. I mean, compressibility is maybe the wrong word, but the dependence of density on temperature we're going to neglect. And we are also going to neglect the effect of temperature on the specific heat. This is by choice. If you would like to, you can model this in our software. I'm just going to forgo this to simplify the model as much as possible. I think this is enough non-linearity. So to speak, this is sort of enough complexity as is. We don't need to, try any further just for demonstration. Perfect. So once again, we have the material properties. We're in advanced. And so next we're going to move on to the actual solution. So here we initiate our velocity. Let's just run this. So, and the velocity and our pressure. Actually, here, so if I were to display our velocity field, I mean this is x velocity, but this is for everything else too. It is 0 everywhere. Now I should say we're defining the velocity field for the solid as well, but what's going to happen is the velocity in the solid is simply going to be equal to 0. So there's obviously no convection in the solid part of the domain. Okay, so here we define we initiate the velocity. Convergence is a variable that simply keeps the convergence history, so we can later display the residuals in a graph. So the convergence plot, I'm sure everyone is talking about. So the next line we initiate our pressure. So we initiate the pressure as 280 Kelvin everywhere. This is obviously going to change throughout the simulation. T old is a variable I only keep because I'm interested in how much the temperature changes in each iteration. So if the change in temperature later on is small, I'm going to stop the iterations. I'll get to this in a second. And here we define the stepping criteria, so the maximum residual of the Navier-Stokes equations, and the maximum number of iterations for the flow problem, for the thermal problem, and also for the general problem. So like I mentioned earlier, what we're going to do is perform so we're going to iterate flow until convergence. Then for that velocity field, we're going to iterate our heat transfer equations until convergence, and we're going to do that sort of sequentially until the solution converges. I believe in this case, I think it's a set amount of times, so it's 10 times, but this is enough for the solution to converge, and the sort of inner iterations have a stopping grid built into them. All right, so let's define this once again, just to be sure. Okay, the U relax is the under relaxation factor for radiation. I'm going to be talking about this in a little bit when I get to how to converge our solution, because radiation is a bit of a nasty habit to oscillate sort of back and forth. Actually, to just blow up very easily. So you almost always need to under relax your thermal or your heat transfer when you're using a radiative boundary condition. All right, so this is the velocity profile at the inlets. It's just a parabolic profile of amplitude, I believe, 5 thousandths. Yeah, so this is just the velocity profile at the inlet. We're going to see it in a little bit. Here we have our configuration factor matrix. So I talked earlier about the configuration factors and what they are between each face of the mesh, between each bit of our boundary. So in general, for larger, this function actually takes a lot of time because it is very computationally complex. It needs to calculate the configuration factor between each face of the mesh that we define, and also it needs to check if there's a screen, if there's another face between those two faces that is screening them. So obviously, I mean not obviously, but our model sort of, you cannot find any sort of the faces are not translucent. They're opaque. So the radiation stops when it reaches a face. It doesn't travel further. So this is simply this argument is, once again, these are the two mesh arrays. So the node coordinates and the definition of the edges. And here's a vector with all the radiating faces. So once again, we don't actually need to compute the configuration factors between every face of the mesh because we can determine which faces are going to be or which boundaries are going to be radiating with each other. So obviously, it's just going to be the outside of the copper pipe that is heated and the top of the channel. So this is exactly what I just said. So let's run this. This will, as you can see, this is going to take like a second. Actually, yeah, it was very fast. It's a fairly small case. So, and here, what we do here is we this is the fluid flow part of the simulation. So we built the Navier-Stokes system for the entire mesh. However, obviously the velocities are 0 for the fluid for the solid domain. So despite building our problem for the entire domain, we're only really solving it for the fluid domain, which means there's no unnecessary overhead for dividing or for considering this sort of zeroed out equations for the solid part. So there's well the definition is what it is, but the computations are on the smallest domain possible. Yeah, once again, we have the inlet boundary condition. So this is the velocity profile that I talked about a while ago, and we have a wall condition. The not need an outlet condition because in our toolbox, any for fluid flow domain or any boundary which is not prescribed a boundary condition automatically becomes an outlet. This is the sort of formulation. This is the way the formulation of our equation works, which is frankly quite convenient. So here we compute the residuals, we plot them, and the fourth figure. This is the stop criterion. So once again, if the residual is under this value, then the iterations will stop. And this is the actual solution of problem. As you can see, we only consider the fluid indices, so we do not actually solve this problem in the solid domain. There is no computational power is wasted. Just wanted to underline that. So despite the code may look a little bit strange, but there's no computational power wasted, which is I think fairly important. So yeah, here we just plot our results, which you'll see in a second. And then what we do here, oh, actually one thing I should mention, here you can see the viscosity is a function of temperature. Like we said earlier, I showed you guys the plot, the viscosity as a function of temperature plot. Wonderful. So moving on, here we iterate the thermal terms. So I mean, if we recall the heat transfer equations, they're linear. So I mean, you would think they only require one iteration since they're linear. But actually, because we have radiation is certainly not linear. I mean, just because you have t to the power 4, but also because sort of you need to iterate your solution at least several times so the proper surfaces heat up to what they actually should heat up. This is sort of sequential, but I mean, I don't think there are any surprises. So this is the thermal problem. We have diffusion. So this is simply, we have diffusion. This is the thermal conductivity in our domain we defined earlier. So the copper part and the fluid and the water part and the channel part have the proper conductivities depending on whether they're copper, steel, or water. And here we add the convection matrix. So as I mentioned, we have those. So obviously, the heat is going to be convected as well. So yeah, this is just the way we call it. We assemble the convection matrix in our software. And here we impose 275 degrees Kelvin, so approximately 2 degrees Celsius on the inlet, so it's fairly cold water. Then we impose also a constant temperature at the inner side of the copper pipe, so it is 1100 Kelvin, which I'm sure you realize is fairly hot, which is going to be radiating and heating up the channel. And here what we do is we tell we tell the solver to include radiation. So we use the configuration factor matrix that we computed earlier. We obviously need the temperatures because we need to determine how much radiation is leaving each face. These two arguments here, I leave them empty. What you can do here is you can define the emissivity and reflectivity of a surface. So by default, the emissivity is 1, so it radiates as a black body would. Excuse me, and the reflectivity is 0, so it absorbs a surface absorbs all radiation that reaches it. I mean, it's very simple to define, but just for this case, I wanted to keep things fairly simple. So here we under-relax our solution, so we only take a part of our solution, and we weigh it with our old solution to limit any oscillations that might occur. I'm going to talk about the oscillations in radiation later because it's actually fairly big problem, but it's very easy to fix, fortunately. And here's the terminal condition. So what this says simply is if the norm of the change in our temperature divided by the norm of the actual temperature, so the relative change of the temperature is small under this value, then we terminate our iterations. So we consider our solution converged. Then we display our solution, and then we also display the viscosity field. Once again, the viscosity is dependent on temperature, so we need to, I mean, I just thought it would be nice to visualize it so you guys can see the effects that it has on the flow. All right, so I think at this time I'm going to take some more questions before I actually run anything. So do you guys, is everything clear? Do you guys want me to explain anything in more detail? All right, someone's typing. Okay, someone is still typing. All right, it's clear. Perfect. All right, thank you. I think we've spent long enough. What happens here? I'm going to run this from the beginning. Perfect. So we should see our results shortly. This is a fairly small case, so this shouldn't take a while. I would just like everyone to know that I'm using a laptop for this simulation. So the computational power required for our toolbox, I mean, granted, this particular case is very small, but just in general, toolbox is fairly efficient. So you can compute cases, even big cases, up to like a few 100,000 nodes on a laptop. You don't have to, invest in a supercomputer or a cluster or anything like that. Okay. So as you can see, initially the velocity has a parabolic profile here because the viscosity is initially constant in the first iteration. And here, as you can see, we've computed the viscosity. Yeah, you're gonna see the temperature in a minute. All right. Actually, let's we can hide the residuals for now. We don't really need them right this second. Okay. So this is still computing, by the way. I'm just gonna talk on these sort of intermediate results. So just with temperature, as you can see, the pipe is hot and it heats up the channel. Sort of the most heat is radiated here, right by the pipe, which is, I mean, obviously you would expect that. It's a sort of physical behavior. And then the further away from the pipe, the less radiation has an impact. So sort of the cooler it gets. We have a constant temperature condition here, which is why the inlet is. I mean, the coldest part is at the inlet. Yeah, and you can see that the fluid, I mean the channel here, because it has much greater thermal conductivity than the fluid, it conducts heat much better. And because we also have convection, excuse me, because we also have convection, if we zoom in a minute, you can sort of see that uh, the sort of iso surface, or iso lines in this case, of temperature are at an angle to the channel because of convection. Sort of the further we flow downstream, the more heat we pick up from the channel wall. Essentially, I'm sorry, this is not maybe the most elegant way of putting it, but I mean I'm sure you guys know what's happening. So is this done? No, we're still computing. Okay, so yeah, this is the temperature field once again. I'm going to zoom in a minute after we're done with the computations. I think this is the penultimate iteration, or maybe even the final one. Yeah, as you can see, the temperature is basically not moving anymore, and the water at its hottest point heats up to like 370, so like almost to the boiling point. Okay, so are we done? No, we're not done yet, but I think we're almost done. All right. Viscosity, temperature, and velocity. So let's just give it another minute. Yeah, this is a model, so obviously this is going to take a little while to compute, but I think we're almost there. Oh yeah, and the residuals also. I mean the temperature is barely changing, so I think we're almost there. All right, so yeah. You know what? Let's just kill the simulation. I think it's converged enough. We don't really have to. Oh, actually, it just finished. So just a few words about the results. Um, this is the convergence plot. We're not really interested, but as you can see, after each temperature iteration, our residuals rise because we have a new velocity. Excuse me, we have a new viscosity because of the change in temperature. So we need to sort of compute the solution again. So this is as you would expect. So here, what I mentioned before, and what's interesting, is that because the viscosity is dependent on temperature, there's not going to be a parabolic profile all across the flow here. So if we sort of zoom in here, you can see this is parabolic. But then as we move further down here, because water has lower viscosity as it heats up, and because the fluid in the top part of the channel is warmer, obviously, uh, the flow is going to more water is going to flow in the top part of the channel because of the lower viscosity, and you can see this effect here. And then we get something resembling a well, not really resembling a parabolic profile, but I mean, you guys can see the results. Yeah, so as I said, the temperature as we move down the channel. Here, because of convection, we sort of an offset from the wall, and the further downstream, the bigger it is. So here the temperature is higher here, and depending on this field, we get the viscosity field. Based on this field, it's exactly what you would expect. The colors are, by the way, the colors are scaled. So we cut off any temperature that is above the temperature of the fluid, just because obviously we wouldn't see anything because the pipe has a ridiculous temperature. 1100 Kelvin. So the fluid would just have it would look as if it had constant temperature because as you can see, the change is fairly. And once again, the change in viscosity is from like, I want to say like 3 to over 16. This is in meters squared per second because it's kinematic viscosity. All right, so I mean this is fairly clear, I believe. Once again, the point of this was not to compute any sort of super physical solution of a particular case, just to demonstrate the capabilities of our solver and what you can do with it. So yeah, let's take some questions at this time regarding just the case itself or the results. Do you guys have any questions? It's quite strange the x velocity does not change too much from the initial profile. It should have increased to the outlet. I mean, the velocity can't. It does increase in the top part of the pipe because you have mass conservation, because it's an incompressible fluid. Or we model it as an incompressible fluid. You have to have a constant flow rate across the channel. So, I mean, we can display the velocity field again. There we go. So once again, you can see that in the regions where the temperature rises, the viscosity drops, so the velocity rises. Here, it's higher in the upper part of the channel, but because of mass conservation, it has to drop in the lower part of the channel. And that's fairly straightforward. I mean, the temperature field didn't really get far from the wall of the channel itself because the wall has high thermal conductivity, but water has low thermal conductivity. So I mean, as you saw in the viscosity field, the larger part of the channel still had the initial viscosity based on the temperature that. Okay, any other questions? Looks like a thermal nozzle, but the velocity does not increase to the outlet. Yeah, I mean, basically. Am I adding energy? I mean, I'm adding energy because from the radiative pipe. So if we were to maybe actually let's see the temperature. Yeah, so if we look at the temperature, obviously, because of the way we defined it, the temperature at the inlet is constant, and it's like at 2 degrees Celsius or something. And then because we gain temperature from radiating pipe, the temperature and so I mean the energy of the fluid is higher because uh, because heat transfer. Yeah, I mean it's the way it's supposed to be. Maybe I didn't understand something. Either the velocity or pressure should have increased. The pressure, I mean, we can view the pressure field. I actually selected the pressure field just because it's not really of interest to us in this case. But I guarantee you the pressure has increased and it's no longer just, actually we can, what we can do is we can do exactly this, except let's see the pressure. Yeah, so this is the final solution after after we're done. And if we sort of go back and initiate our solution again and just run one iteration, because it actually for constant viscosity it converges really fast. So if we run one iteration of the flow problem, it's still computing, give it a second. Perfect. Yeah, I'll disregard the error. And now if we go back to our pressure, do we still have the original pressure? Yep. So let's save this to the left side of the screen. All right, and if we display our pressure, that's weird. Oh, maybe it's because the. So let's do it this way. Boom. All right. And if we display our pressure now, yeah. So you can see. I mean, you can see the difference in the angle of the pressure isolines, or the pressure contours, because once again we have flow from going downwards a little bit. All right. So I mean, it also depends on the Reynolds number. This flow is actually very slow, so it's. I mean, the effect is there. It's maybe just not very visible. It's you'd have to fine tune the parameters. Once again, my goal here is not to maybe explain everything. It's more to just explain the solver. All right, wonderful. So moving on, we're going to wrap up this case. And we're going to run this here. Let's just run this right away. I think we're running a little bit short on time. What this is a essentially a cylinder inside a cylinder. All right. So what we have here is the inner cylinder is heated from the inside. It has a temperature of 1,000 Kelvin. And then it radiates out to this cylinder. So obviously what would happen in a physical solution, or in the physical world, the temperature of this outside cylinder would eventually become the same as the temperature of the inside cylinder, assuming, of course, that there's no energy exchange with the outside environment. But this is actually tricky, numerically speaking, because what happens is if you prescribe a zero Neumann boundary condition here, so if it's an adiabatic wall, when you have a flux here, basically you would have to have a flux equal to 0 here, because if you didn't, then because you're simulating a stationary heat exchange, what would essentially happen is your simulation would instantly blow up, because you would have a heat source and there would be no heat sink. So the resulting temperature for a stationary solution of this case would be infinite. And because what you have here is the radiative flux, which, if the temperatures are the same, is very small, obviously, but for numerical reasons, this is not the physical world. This is a mesh. This is discretized. What happens is that there's a small flux, and even such a small flux, because of the stability reasons I mentioned a second ago, the simulation blows up instantly. So in this case, what you need to do is you need to stabilize your solution by adding a way for the heat to escape. So this is the outer boundary is not actually a zero Neumann boundary condition, but it's a Robin, a convective boundary condition. But the coefficient that we saw in the equations, which determines the flux depending on the difference between the temperature of the solid here and the reference temperature outside. So because this it's very small. So because this coefficient is very small, it doesn't significantly impact the actual results, but it stabilizes them, so you don't get it doesn't blow up for the reasons I mentioned before. So actually, let's see what happens if let's try to blow it up on purpose. So for example, if I completely comment out, and if we set the initial boundary, initial temperature to 1000 for the entire domain, yeah, so let's run this first. It takes a little while, the diffusion matrix to assemble, and also the configuration factor matrix, in this case, takes a little while because it's a finer geometry. Yeah, so let's visualize this field. And you can see it's a constant temperature of 1000. And this is a fine mesh too. Uh, what happens when we run run one iteration, even with a very small under relaxation factor of like this 0.003, it's very small. Even with this, yeah, you can already see because there's a unbalanced heat flux. We instantly get a ridiculous temperature of like, I mean, and it's a negative temperature too. So apparently numerical error in the heat flux was negative. Um, so yeah, our simulation blows up instantly. Even as I said, even with a very very small under relaxation factor. So the solution is actually only a small fraction of what it would be without it. Um, so what happens is we stabilize the solution at least a little bit. I mean, in this case, we can actually describe the reference temperature as 1000. Um, and we'll see what happens if it actually converges. Maybe it won't. Yeah, see, even despite our stabilization, there's a small numerical error. As you can see, it's tiny. It results in like a fraction of a degree of error. Um, but it's there nonetheless, right? So, um, if we didn't have the row boundary at the outside here, as you saw, it just blows up. So, I mean, usually in real life applications, you don't really have I mean, every sort of body has both a heat source and a heat sink, essentially. So the problems with stability are definitely nowhere severe in this case. I purposely chose it to sort of exacerbate these stability issues. So in general, what I would recommend is always under relax your solution at least a little bit. And I mean, then if it blows up, if it still blows up, then you can stabilize it. Uh, a sort of a common behavior, regardless of the actual sort of temperature here, is that if the solution were to blow up, what would happen is this bit heats up too much, so it radiates out a lot of temperature, and this bit is cold, so it absorbs a lot of temperature. So in the next iteration, this one would be very cold, and this one would be very warm, and there would be colder and warmer than in the previous iteration, and this would sort of oscillate back and forth, uh, and the temperature amplitude would increase, and this would blow up out of proportion or out of it would just blow up, and we wouldn't get convergence. So once again, what you need to do is employ under relaxation. Once again, for real life applications, this is nowhere as severe as in this case, but it still can occur. Actually, our company, we had a project because our company, outside of offering the software and developing the software, we also do we consult for other engineering companies. So we do basically simulations on demand. And so it was a heat exchanger. I don't want to get into the details to bore you, but it was a real life application. It was a very realistic case that the company is actually building, and for that case, I think it was somewhere in the area of a part of the heat exchanger had in the area of like 12 or 1300 Kelvin, and the colder part had in the area of 900, and we needed to employ an under relaxation factor of like 0.2, which I mean for fluid flow it's fairly small. For radiation, actually, it's fairly large. There have been cases. I've worked with cases that require even an under relaxation factor of like 0.05 or like 0.02. It's very case dependent. The rule of thumb is start at like 0.5 or something, and if it doesn't converge, then try a lower one. Okay, so I think we've taken up enough time. Let's maybe take some questions, and I'll let you guys go. So, do you wanna ask me about anything with relation to the radiative solver or maybe your software in general? Now is the time. All right, I see somebody typing, and they're not typing anymore. All right. Will this webinar be available as a video afterward? Yes, this webinar is going to be uploaded to our YouTube channel. If you type QuickerSim, the name of our company, into YouTube, you can find our channel. We have some tutorials there as well. And this video should be uploaded. I mean, we have a long weekend coming up right now. But anyway, it should be there probably on Monday. But it will definitely be uploaded within the next week or so. Any other questions? I see some people typing. All right, maybe not. Going once, going twice, going 3 times. All right. So thank you for bearing with me up until this point. Actually, we do have questions. Is it possible to apply the radiation toolbox to other cases, gases? Yes, absolutely. So our basic flow solver is incompressible, I'm afraid. But I mean, you can define any material properties as you wish. Obviously, it's very general software. So if you can model your gas as incompressible or the flow of it as incompressible, then sure. I mean, what I'm getting at is so the flow is always going to be with a constant. The flow is going to be always with a constant density, but if there is no flow, then you can simply, I mean, when we bring up and sharing, when we get back to the presentation here, last page, or the second last page. Yeah, so as you can see, the density is simply a term in the equation, so we can multiply the appropriate matrices by a non-constant density, and you can definitely model sort of this fully. Yes, the toolbox is available. You can download it from the link in chat. It's quickersim.com/cfdtoolbox. There's a free version, and if you email us, we can send you a trial for the full version. But I mean, obviously, you would need to buy the full version to have it perpetually. The Radiative solver is in the full version, so if you would like to check out the Radiative solver, then you will need to ask us for a trial. Any more questions? All right, wonderful. So thank you all very much. We ran a little bit over the scheduled time, but that's okay. So once again, I encourage you to download our software from quickersim.com/cfdtoolbox. I use it in my actual engineering work. As I said, I don't just develop the software. I also use it for consulting purposes. So it's tested in the field, so to speak. We've computed several hundreds of real life cases on it, if not thousands. So it's fairly well validated. Thank you for listening. I hope I didn't bore you guys too much. And please check us out. We're on Facebook. We're on LinkedIn. We also have a YouTube channel, as I mentioned. We have lots of videos there, tutorials, and other webinars. And I hope you guys can join me in the future. We're going to be hosting these webinars every few weeks. We'll be talking about the various functionalities of our toolbox. So once again, thank you for listening, and goodbye.